to have a magnetic dipole. What does that mean? It's nothing but, so magnetic field means this is, I can assume this is north and this is south. That means I can assume this is north and this is south. It means if I pull it this way, once I leave it, it's going to fall back. So we are talking about the third derivation, magnetic dipole in an external magnetic field. So this is my magnetic field direction B. Which way is magnetic moment, magnetic dipole direction? Is it this way or this way? South to north, which means it will go this way. There it is minus to plus, so this will be south to north. It means magnetic field direction is this way, magnetic dipole moment is this way, so this is my theta. Theta is the angle between M and B. We'll try to turn back, align along the B direction. So from this I can say tau is equal to M cross B. Potential energy stored is equal to rotational work done. Work done to rotate will be integral of tau dot d theta. Right? So if you don't understand this, take it as work done is force into displacement. Right? So this is for linear. Don't have to write this in your examination, it's only for your understanding. So this is for linear work, this is for rotational work. So in place of force you have tau, in place of displacement you have d theta. Tau can be replaced as mb sin theta dot d theta. So after that do the same thing, mb cos theta, that will be minus m dot b. But for moving from theta 1 to theta 2, then it would be tension Gu is equal to integral of mb sin theta d theta, theta 1 to theta 2, mb cos theta So sometimes you would use this formula, sometimes you would use that formula depending upon what you are doing. Okay. So if you have two angles given, how much work you are doing, right? What it means is, so what is the potential energy stored in this? mgh. but that is if you take from the ground, right? Let's say I'm moving it from here to here. That means it will be mg h2 minus h1, right? This is h2, this is h1. So h2 minus h1 will give me the work done from moving from here to here. So same thing. So if you are moving it from the base, right, then it will be like this, just like mgh. Whereas here it is mg h2 minus h1. That's all. It's the same thing. So you are moving it from certain angle to certain angle. So you will make use of all these things for your numericals. Usually theta 1 is equal to 90 degree, as 90 degree is taken as the reference. That means if I put theta here, this will become cos 90 will become, cos 90 is 0, right? So that means it will be u is equal to minus mb cos theta, because you are taking cos theta 2 as theta. So you will arrive at the same formula like this. So the special cases would be, special cases. So if I take this as the magnetic field direction B and the magnetic dipole moment, so at this point, if it is 90 degree, right, cos 90 will be 0. So at the reference point, u will be 0. So theta is equal to 90 degrees, so u is equal to 0. What if it is aligned this way? Then theta will be 0, right? Because magnetic field is like this, magnetic dipole moment is also this way. That means theta is equal to 0. So this is second case. So theta is equal to 0 means cos 0 is 1, which means u is equal to minus mb. Okay. And then suppose if the magnetic dipole moment was this way. So what is the angle between? B is always this way, so m is this way now. So that means theta is equal to 180 degree. So cos 180 is minus 1, minus into minus plus, so u will be mb. Anybody having any doubts here? Special cases? Any doubts, any issues? I'm simply substituting the theta values over here. Now important question. When you leave it, right? When I leave this pen, right? It's going to fall down to the ground, which means I will take the ground as the reference, right? If I leave this bar magnet, is it going to go and stand like this, or is it going to go and fall like this? It's going to fall like this. Then why would I take the reference as 90 degree? We would have done the same thing over here also, right, in the previous chapter. So for some reason we are taking the reference point as 90 degree. Okay, it's a little bit involved topic. We'll come back to that later. But right now what I can say is the reference point is your choice. Why? Because did somebody say that I have to take that as reference? What if I did the experiment on the table? Then if I leave it, it's going to fall only to the table, right? That means this is my reference point now. Okay. Actually, we are standing in the third floor. So if you really want to calculate from the Earth's surface, then I have to calculate the distance from the ground. Are we doing that? No. So that means that reference point is always your choice. So in a given experiment, you have to determine what is your 0 point, and then you have to stick with that. You following what I am saying? So don't get confused why you are taking this as the reference point. Is that clear? Because depending upon the problem, right? We may have to use different reference points. Zero. I am taking this as a reference point, I am getting US 0. Yeah, but in this particular, case, we are always, the book always takes this as the reference. So let's follow the same thing. If you can take it differently, then all the things will change. As I said, it's a little more involved topic. I will take it separately. Okay, it's there in your second chapter, but you need to go back to the potential topics. So because of that, usually I would have thought that this point should be 0, right? Instead I'm getting a minus MB. Okay. The way you can understand that is, suppose if I am doing experiment on the table, right? What would be that point for me? It would be positive or negative? Negative, which means if I calculate the potential energy there, it will be negative. Is that clear? Whereas here it is positive. So same story here. Since I have taken this as reference point, this becomes negative. Okay. So don't worry too much about it. In case if they ask you the special cases, you have to do this. Okay. So that's your third derivation. Any doubts here before we pass on to the next one? No issues. Okay.